Hey guys, hope everyone's having a good weekend. Let's do this calculus thing. Okay, so whenever we want to find a point of inflection, what we want to think about is when is the second derivative equal to 0. So if this is our function, our first derivative, 20x to the third minus 5x to the fourth. And then the second derivative would be equal to 60x squared minus 20x cubed. And when is this going to be equal to 0? Looking at both of these, the greatest common factor is 20x squared. That would leave us with a 3 from the 60x squared and an x from the 20x cubed. And when will these things be equal to 0? Now, in order to be a point of inflection, the second derivative has to equal 0, and we need to have a sign change of the second derivative. So maybe x is equal to 0 and x is equal to 3. But if we look at where these factors come from, x equals 0 comes from this factor here. The exponent is even, so there is not going to be a sign change. There is going to be a sign change here because that exponent is odd. So the only x value that is a point of inflection is the one that has an x value of 3, and that's the only answer where the x coordinate is 3. We're looking at a picture of the function. So if we look at a picture of the function from 2 to 7, our graph starts out concave up. And then the graph is concave down. So somewhere in here there's going to be a point of inflection. Then our graph is concave down. And then somewhere around here the graph changes to concave up. So it's concave down and then it's concave up. So somewhere around here there's going to be a point of inflection. Then our graph is concave up until the graph is concave down again. So concave up to concave down. So somewhere around here there's going to be a point of inflection. So there are 3 points of inflection from 2 to 7. This one was a little tricky because in order to take the derivative, we should rewrite this as x to the negative 2 minus x to the negative 3. So now that I've rewritten it so that we can take the derivative, y prime is equal to negative 2x to the, when we subtract 1 from that exponent, we get negative 3, plus 3x to the negative 4. Looking for points of inflection, we want the second derivative to be equal to 0. Positive 6x to the negative 4 minus 12x to the negative 5. When is this going to equal 0? Well, let's factor that. Both of them have a 6. X to the negative 4. I'm left with 1 minus 2x to the negative 1. When will this equal 0? Let's rewrite this so that it is 6 over x to the 4th. When will that equal 0? Well, I can't take 6 and divide it by anything and have it come out to be 0. So this doesn't give me a point of inflection. But can I take 1 minus 2 over x, which x to the negative 1 is 1 over x? When will that equal 0? Well, if we add, I don't know why I'm wasting time changing colors. If I add this to both sides, so 1 is equal to 2 over x is equal to 2. Alright, questions 4, 5, and 6 all deal with the same picture. And let's just be careful because we are, in this case, looking at a picture of the derivative. If we want to write the equation of a line, we need a point and a slope. The point that we have is 3, 5. The slope, if we're looking at a picture of the derivative, what is f prime of 3? So the slope the derivative at 3 is equal to, well, here's the derivative, here's the next value of 3. At 3, the derivative is 2. So f prime of 3 is equal to 2. So the slope of the tangent line at 3 is going to be 2. Using point slope form, y minus y1 equals m, x minus x1, we have y minus 5 is equal to 2 times x minus 3. C. When we have a point of inflection, let me just do this so that we can see 5 and 6 in the same. Okay. So when we have a point of inflection, and we know the derivative, we want f prime to change from increasing to decreasing, or vice versa. So the graph starts out going up, then it's going down, then up, then down, then up, then down, then up. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. 6 points of inflection because we have 6 changes: up, down, up, down, up, down, and then back up again. So 6. Here's an x value of 0. Here's an x value of 8. Here is an x value of 6. Up until, that's not what I wanted. Up until here, all of these derivatives are positive. And then from 4 to 6, the derivative is positive. So from 0 to 4, we have positive, and then a horizontal tangent. And then, let's put 4 in there too then. And then from 4 to 6, we have positive derivatives. And then from 6 to 8, we have negative derivatives. So my function is doing some stuff. It's increasing, and then at 6, it decreases a little bit. So at 6, f prime changes from negative to positive. And I'm looking for the absolute minimum. No matter what the initial y value was, all of this increase and then a little bit of decrease is going to leave our absolute lowest value at 0. Because the derivative increases from 0 to 4, from 4 to 6, and then it decreases a little bit. The function decreases a little bit from 6 to 8. At the derivative, let's think about what we have. So I'm going to label everything that I can from this derivative. From this derivative, I can say that this point, the derivative changes from negative to positive. So if the derivative changes from negative to positive, we would have a minimum. At this point, the derivative changes from positive to negative, so we would have a maximum. At this point, the derivative changes from negative to positive, so we would have a minimum. If we thought about what these points were, at these points, the graph of the derivative changes from increasing to decreasing and then decreasing to increasing. So both of those points would be points of inflection. So now looking at the answers. A, 1 relative maximum and 2 relative minimum. Because we have 1 max and 2 minimums. Point of inflection, y double prime is equal to 0. Y prime, 3 times a third is 1 x squared plus 10x. Y double prime, 2x plus 5. When is this equal to 0? This was a 10. That's what you get for rushing. When will this equal 0? When 2x is equal to negative 10, or when x is equal to negative 5. All right. dy dx, we have an implicitly defined function. So the derivative of the left side, dy dx, is equal to. Now we need to use the product rule. So we have f times g. The derivative of the first, 1, times the second, plus the first times the derivative of the second, plus 2x. And then the derivative of 1 is 0. Let's get everything with the dy dx on one side. So if I subtract over my x dy dx, I would have dy dx minus x dy dx is equal to y plus 2x. Factor this out. So let's factor out dy dx, and it's equal to 1 minus x is equal to y plus 2x. Dividing both sides by 1 minus x, dy dx is equal to y plus 2x over 1 minus x. We notice that there is a y in our derivative. In order to find dy dx when x is equal to -1, we need to know what this value is for y. We're told that x is equal to -1. So everywhere in our original implicitly defined function, we're going to plug in -1. Y equals, well, plugging in -1 for x, -y, plus 1, plus 1. -1 squared is 1. 2y equals 2. Y is equal to 1. So now the derivative at the point -1, 1 is equal to 1 minus 2 over 1 plus 1. So I plugged in -1 for x and +1 for y. At a point of inflection, the second derivative has to equal 0 and there has to be a sign change. So the zeros that we have are 0, -1, and +2. But there also has to be a sign change. So this exponent is odd. There will be a sign change at 0. This exponent is odd. There will be a sign change at -1. This exponent is 2, so there will not be a sign change at 2. So -1 and 0 are the only x values where the second derivative is equal to 0, and there will be a sign change of that second derivative. Alright guys, hope you had a great weekend. I can see you whenever. Email me if you have any questions. Come by and see me. I'd be happy to see you.